In this problem, we want to start by finding the critical value t sub alpha over 2 used for finding the margin of error. So there's two ways to do this. You can either use a table of values, or you can use your calculator if you have the inverse t function. So what I'm looking for is I'm going to press second and variables, and the fourth choice, hopefully, this is going to be the easiest way to do this, is to find the inverse t function. So let's assume for the moment that you have that, and if you don't, you may want to skip ahead to where we look at the table. So inverse t, what I'm going to do is I look at what is my confidence level. In this problem, it's 99%. And so I'm going to block off the middle 99% because it's a confidence level, so it has to be in the center. So that means that this is going to be my t value, and this area is 0.5%. Because we had 99% in the center, that leaves 1% for the two tails. We cut that in half, and that's just 0.5%. So we're going to find t sub 0.005. So to do this in the calculator, I'm going to do inverse t, and I'm going to say, what is the area on the left-hand side? So that is going to be 1 minus 0.005, or you could subtract that and get 0.995, either way. And then we're going to put in the degrees of freedom. So this is where I have to look at the sample size, and that's 36. So I'm going to say my degrees of freedom is n minus 1, and that's going to be 35. So I put a 35 in there. And then when I get my result, I get 2.72. So that's my critical value by using the calculator and rounding to 2 decimal places. Now, if you have to look this value up in a table, then what you're going to do is I'm going to take a look at this t table that I just grabbed off the internet. And let's make this a little bit bigger. That's interesting. All right, so what I'm going to do is look to see what is the area in one tail. So I found a table where it just gives the critical value for a one-tail test. I know that I have 0.5% in one tail. If I had a two-tail table, then I would use 1%, and it would give me the same result. So I look at 0.005. So I'm looking at this column, and you can see on the left-hand side, there are the degrees of freedom. So I'm going to have to scoot down to get as close as I can to 35, which is my degrees of freedom. So let's scooch this down. And we wanted the second to last column, 0.005. And so what I see here is that I don't have 35 degrees of freedom. I have 30 and I have 40. So when you have to choose between those, you go with the smaller one. And then we're going to go across here and get 2.75. So that's a little bit different. But my math lab knows that some people are using a table and some people are using a calculator. The calculator value is more accurate, but you know, what can you do if you don't have that feature on your calculator? So then we use this for the table, and MyMathLab will accept both of those answers. It knows that there are multiple possibilities for this. So that's how we do that part. Okay, so now we want to calculate the margin of error. There's a formula for this, but there's also a feature in your calculator that will find this for you. Since we're working with the t distribution, we're going to use t-interval. And so I'm going to press Stat and go over to the Tests menu, and I'm going to skip down to number 8, and that's t-interval. Make sure you're choosing interval and not test, because that's number 2. We will be using that when we get to hypothesis testing, but right now we're using interval. So we're going to choose number 8, t-interval, and everybody will have this on their graphing calculator, so you don't have to worry about that. The only thing that's possibly missing is that inverse t. So now that we're there, we're going to look at what our choices are. The first choice is, what is your input? Your choices are data or stats. In this case, because we know the statistics, X bar and S, we're going to choose stats. And then it's going to ask us for X bar. If it still says list, you need to make sure that you move over to stats. So now we're going to put in X bar, which is 3,180.6. SX is just your value for S, which is 700.5. And then the sample size, not the degrees of freedom, but the sample size here is 36. And then we put in our confidence level, and that gives me 0.99. So now I go ahead and calculate, and my results are 2,862.595698 to 3,498.604302. And that is our confidence interval. So I think the next question is going to be, what is the confidence interval? And that's going to be our answer for that. We're going to go ahead and round that appropriately. But now we want to know the margin of error. So what we want to do is picture this where we have X bar in the middle. We have our lower limit for our confidence interval and our upper limit. So what are the values? Well, we know X bar is 3,180.6. The upper limit is the 3,498.604302. And my lower limit is 2,862.595,698. Okay, squeeze that in there. So in order to find the margin of error is really just the distance from the center, which is our sample mean, to the lower limit, or we could take the upper limit to the sample mean. Either way. So either of these is the same. They're both the margin of error. So you just subtract whatever way is more comfortable. You're probably using the calculator. It probably doesn't really matter at all. So I'm just going to take X bar minus the lower. And we want to round this to 1 decimal place. and I get 318.0, rounded to 1 decimal place. So that's my margin of error. Okay, so in part C, now I want to find the confidence interval estimate of mu. So I went ahead and so we're finding the confidence interval estimate of mu, and I put in the confidence interval values, the lower and the upper values that we found in the previous part. So once we get to part D, it says to write a brief statement that interprets the confidence interval. So what we're looking for is that we have a 99% confidence that the actual value of the population mean is falling within the confidence interval that we found. That population mean is not going to change. It is what it is. Maybe we got a good confidence interval, maybe we didn't. So we are looking for A. One has 99% confidence that the interval from the lower bound to the upper bound contains the true value of the population mean weight of newborn girls. So that's what I'm looking for in my answer there. I don't want to say that there are 99% of the sample mean weights, because that's not what we only found one sample mean, so it's not that. In C, it says there's a 99% chance that the true value falls between the lower bound and the upper bound. And that sounds pretty similar to A. But here, what we're saying is there's a 99% chance of the population mean falling somewhere. And there's not a probability about that. It is what it is. And it's, did the lower and upper bound wind up capturing that actual value of the population mean? So that's why we don't want to choose C, even though that's very tempting. And then in D, it says one has 99% confidence that the sample mean weight is equal to the population mean weight. No, we do not have that level of confidence. So if we got a biased sample, it might be a bad estimate. So that is definitely not correct. So that's how you do that problem.